In March 2026, the DeepReinforce team released a paper detailing a system named GrandCode, achieving Grandmaster level in competitive programming via agentic reinforcement learning. For years, competitive programming has stood as one of the hardest barriers for artificial intelligence to cross. While models like AlphaCode 2, OpenAI's O3, and Gemini DeepThink have posted impressive scores, they achieved those results by evaluating historical problems offline, well outside the pressures of a live competition. Live Codeforces contests impose severe, unyielding constraints. Solutions must operate within tight memory limits and strict execution times, and they must perfectly navigate hidden edge cases designed specifically to break fragile logic. A zero-shot language model generating a single pass of code inevitably fails here. Once a logic error occurs early in the generation, the mistake compounds, and the model has no mechanism to recognize or correct it mid-execution. Solving these problems requires a system that can continuously verify its own work and correct its logic dynamically, rather than relying on rapid text generation. GrandCode is the first artificial intelligence to systematically defeat top-ranked human programmers in live, real-time Codeforces Division 1 and 2 contests. During 3 live rounds in March 2026, the DeepReinforce team deployed the system under 3 anonymous accounts: Avery Jones 1, Yokiko, and Vortex 1. This composite image of the live Codeforces standings shows the results. In all 3 distinct competitions, the GrandCode accounts ranked first overall. The system operated entirely undetected, submitting solutions faster than legendary human grandmasters under strict time constraints. The researchers achieved this performance by moving away from standard large language model prompts. Instead, they built an orchestrated multi-agent reinforcement learning loop. GrandCode functions as a coordinated ecosystem of specialized agents rather than a single coding model. The architecture relies on a central main solver that communicates cyclically with a hypothesis module and a parallel test case generator. The test case generator serves an adversarial role, producing extreme edge cases built to intentionally break proposed solutions. By running these tests in parallel, the system isolates code that is logically sound but computationally too slow. It catches time-limit-exceeded failures internally, long before the code is sent to the official competition judge. This multi-agent scaffolding forces the system to rigorously attack its own reasoning. It mimics the scratchpad process a human grandmaster uses to verify an algorithm's efficiency before writing the final code. The most critical safeguard against logic hallucinations happens at the very beginning of the loop: hypothesis generation. This workflow diagram details the process. Before writing full solution code, the agent must generate a structural or mathematical conjecture about the problem, shown here in the yellow Propose Hypothesis box, proposing an equation for K-max. The system then moves down to the verification step. It generates small random data inputs, usually arrays of 8 items or fewer, and computes the exact answer using a simple brute force solver. At the compare node, the system checks its proposed hypothesis against the brute force results. If outputs do not match, it rejects the hypothesis and triggers a revision loop. Only mathematically proven conjectures reach the hypothesis validated box. By anchoring the initial logic to brute force mathematical proofs, GrandCode prevents compounding errors from derailing the complex, long horizon code generation that follows. Training a multi-agent loop this complex required a new optimization engine, which the researchers call Agentic GRPO, or Group Relative Policy Optimization. The primary bottleneck in multi-turn agentic reinforcement learning is severe off-policy drift, which is driven by delayed rewards. Consider the credit assignment problem. If an agent successfully submits a final block of code at step 10, the system needs a way to pass that positive reward signal all the way back to the specific hypothesis it generated at step 1. Standard algorithms struggle with this, applying immediate rewards across asynchronous stages and assigning credit incorrectly. Agentic GRPO solves this by mathematically combining immediate, step-by-step updates with delayed, retroactive corrections once the final outcome is known. Because it assigns credit precisely across long rollouts, the system can adapt online, learning from live environment feedback while the contest is still running. Agentic GRPO is the mechanism that binds separate language model prompts together, creating a unified, self-optimizing policy capable of real-time adaptation. To see how this architecture handles adversarial pressure, we can examine the raw submission logs from the live contests. Looking at the submission timeline for the Avery Jones account during round 1087, the timestamps under columns A through F reveal a rapid, unbroken sequence of successful solves. This page details the specific verdicts for those submissions. The pre-tests passed column confirms that the internal verification loop successfully filtered out errors, while the low memory usage and millisecond execution times prove the code was highly optimized. We see the same consistency in the Nebius Round 2 contest. The Yokoko account secured the #1 rank with a total of 15,008 points, dominating a combined field of Division 1 and 2 competitors. These leaderboards confirm the results. Combining delayed correction reinforcement learning with continuous internal verification solves highly constrained logic problems faster than the most skilled human programmers. The architectural design of GrandCode applies to challenges well outside of competitive programming platforms. The hypothesis and verification loop provides a framework for automated algorithm discovery and complex hardware-level optimization, where mathematical exactness is required. Furthermore, Agentic GRPO's method for handling delayed credit assignment provides a roadmap for training AI on complex enterprise software tasks that demand multi-step logical deduction. Any generalized reasoning problem that requires continuous self-correction and long-horizon rewards can now be mapped to this optimization structure. By architecting the right multi-agent reinforcement learning scaffolds, AI systems have breached the highest thresholds of human analytical performance in real-time environments.